Hi class, so this is a video solution set to the academic conference for week 3. We're looking at it here. Consider a population data set of students' final exam grades from a large statistics class. And specifically, the number of students in the class is 100, capital N indicating the population parameter. The population data set has the following characteristics. There is a population mean of 78, a population standard deviation of 5, and the data set is dramatically skewed left, as most grade distributions are. Suppose you were to randomly sample from this population of n equals 100 a sample size of 45. Again, small n here indicates a sample. Let's see if this highlighter works. Yeah. So from your sample of 45, you calculate a sample mean. We denote that as x bar. Now suppose that you were to repeatedly draw samples of size 45, and each time you calculated a sample mean for those 45 students. So what I'm talking about here, if I take my pen, is a bunch of sample means. Okay, every time you take that sample, you calculate an x bar, and every time you take that sample, you take it's a random sample, so x bar is a random variable, and x bar, the collection of all possible x bars from sample size of 45 from my population of 100 would make up what's called a sampling distribution for the mean. So question 1 says, write the formula necessary to calculate how many unique samples, combinations of 45, that can be drawn from a population of 100. And that formula is a combinations formula. You can find it in the corresponding chapter in the textbook, and I will write it here as well. If I have a population of 100, then the numerator is 100 factorial, so that's 100 times 99 times 98 times 96, 7, and so on. Of course, a calculator, every basic calculator has that function. And if I'm choosing 45, then the denominator is going to be that numerical choice value. So I'm taking 45 samples of 45 from that 100, and the remainder here is 55. And so this is the formula. Now my Casio, my simple Casio calculator can't calculate that. It's an extremely large number. So I'm not actually asking you. So you'll have hundreds of millions of possible samples from this. So that's your answer to number 1. And many of you, of course, wrote that out correctly. If you were to take all possible samples of 45, so you exhaust the population in the sample size, and calculate x bar for each of those samples, what shape would the distribution of those sample means be? So what I'm talking about here is if you organized all of these x bars, okay, on the horizontal axis are your values for x bars, and on the vertical axis is your probability, right, of x bar. And most of the time we don't write that out, but the vertical axis is always a probability. In fact, to clean it up, I'm just going to get rid of it. But we know we're talking about a probability distribution. Well, what would this thing look like? What shape would it take on? Well, there are some characteristics that I know right away from this sample. I'm drawing it as a normal distribution, a mound-shaped distribution, and the reason is because of the central limit theorem. Right? Since n is greater than or equal to 30, I know by the central limit theorem that the collection of sample means drawn from this population will be normal, regardless of the population distribution, which I said is dramatically left skewed. Okay? Moreover, number 3, right, what would the mean of the sampling distribution equal? Well, the other property that we know is that the mean of all possible sample means has to equal the population mean, which I mentioned above was 78. So the population mean, oops, sloppy. It's hard to write with this pen sometimes. The mean of all sample means, right? In other words, the mean of the sampling distribution is equal to the population mean. That is a property that will always hold, regardless of the sample size, regardless of n is 30 or more. That will always hold, that the mean of sample means is the population mean. Now, moving on, what would the standard deviation of the sampling distribution equal? And the standard deviation of a sampling distribution is also called a standard error. All right, it's more frequently called a standard error in the statistician literature. Now, your textbook, I'm not sure, it kind of shies away from that term, but that's the traditional term. So the standard deviation of the sampling distribution equals, okay, and I will write it, it's sigma sub x bar, and that equals sigma, the population standard deviation, divided by the square root of n. Right, so this number is the population standard deviation, and this is 45. The population standard deviation was 5, divided by the square root of 45, 0.7454. So notice, a standard deviation is an average deviation from a mean, right? So in the population, we have a mean of 78, and on average, grades deviated from that mean with 5 percentage points, right? 5 grade percentage points. But here, since I'm taking samples of 45 and calculating sample means, my variation around that mean is going to be a lot less. In fact, it's 0.7454. Right, in comparison to 5. And so a sampling distribution is going to have strictly smaller variance than its parent population. 4, what would the standard deviation of, that's 4, I'm sorry. 5, what is the probability of getting a sample mean greater than 80 from a sample of n equals 45? Okay, this is going to require me to use my knowledge of the normal distribution. Let me pause this for a minute and clear the slide. Okay, we're back. So what I've done is just recreate this graph of the sampling distribution from the mean. Notice that the standard deviation of this graph is 0.7454, like we just calculated, and I've included 3 standard deviations above the mean here. Okay, and so the area that we're looking for is 80 and above, right, or greater than 80. It doesn't matter if you include 80 or not, because with a continuous distribution, the probability of getting exactly 80 is effectively 0. So it doesn't matter. We're looking for the probability that x bar is the following. Or it could just be greater than 80, like I said, it doesn't matter. Well, we know that this is going to follow a z distribution. Okay, we have the population standard deviation, which is 5. We know it's normal by the central limit theorem. The z distribution is always centered at 0. And now what we need to find is the z-score for 80, which is our frame of reference, okay, minus the, again, that's sloppy, the mean of this distribution, which is 78. Over the standard deviation of this distribution, which is 0.7454. And if we do that, 80 minus 78, 2 divided by 0.7454, we're going to get 2.68 as a z-score. That's a pretty large z-score. And so we go to the z-table, and I'll show you the particular z-table that I like to use. Let me pause it again. Alright, so that z-score of 2.68, if I look toward my z-table, this is the cumulative z-table. I did post this in the conference area in response to a student's comment. This is pretty simple. You look up any z, and you can look up your negative values from about -4 to +4, 3.99, and -3.99. And whatever value you look up, it's going to give you the area to the left. So the probability of being less than that. And so if I'm looking up 2.68, my first to one decimal place, right, is right here, 2.68, 2.6. And to the second decimal place is 0.8 up here. And where those two intersect is 0.9963. So 0.9963, if I go back here, is all this area, 0.9963. So 1 minus that is the area that I need, which is 0.0037. So about 0.4% of the time, you'd get a grade of greater than 80 given sample size of 45. So very seldom, right? It's very unlikely. And that's because, you know, if you're taking a sample size of 45, which is pretty large relative to the population and relative to the central limit theorem criteria, you're going to be pretty close most of the time, right? 95% of the time we know with the empirical rule will be within 2 standard deviations from the mean. And so this is obviously just short of 3 standard deviations. We wouldn't expect it to be a big number. So 0.0037, if we go back to this, is the answer. Now, a student at the 90th